Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So for today, really I want to talk about thermal stability and what does that mean? Basically I'll start off by defining what thermal stability is. Why do we care about thermal stability? And then once we understand what it is, it's how do you measure it? It's a little trickier than what you might think. And then how do you design to ensure that you achieve thermal stability? And then we'll sum it up and go through some differentiators at TRM.
Okay, well, thank you. And to get started then, what exactly is thermal stability?
Well, it's a great place to start. So when you talk about a topic, it's always good to have a good definition of it. So thermal stability really comes down to how much does a unit's performance change with the change in temperature? Thermal is temperature. So does the unit's performance change when the operating environment temperature changes? And usually parts do change with temperature. As you go into some of the laws of physics here that drive this, it's inevitable. It is not a completely independent parameter. So the key here is to understand what drives it and how do you mitigate it. The next bullet down there is why do we care? Really, we care a lot because we assume that things are going to be the same unless we know they're going to be different. Which is sort of a philosophical way of saying that we have to understand what's going to change and how it's going to change with the environment that it's in. So thermal stability is always critical. Temperature is always moving up and down. There are some rare cases where you get a controlled environment, but it's rare. And really, for every system performance, thermal stability is always on the table. It's something that we always work to design towards because we don't want things to change from a performance standpoint due to the environments that are being inflicted on it. So understanding what it is and how to control it is absolutely critical.
Okay, well, thank you. And now that we have a better understanding of what thermal stability is and why it's so important, what are the best ways to measure it?
So measuring is easier said than done because the things that you want to measure thermal stability with are affected by temperature. Things like cables, RF cables that go in and out of devices have materials in them that are not stable over temperature, and therefore, so if we're going to take a device and put it inside of a thermal chamber and get it hot and get it cold, those cables that are connected to that are getting hot and getting cold. They're going to add error that we could attribute to our device, but they're really coming from the cables. So how do you separate that? So usually what we do here at TRM is we modify thermal chambers to make sure that we can get all of the cabling outside of the chamber or the environment with just having the unit inside the environment. What this leads to is some very, very custom fixturing. I think you have to think this through to really understand what is the device that you're measuring and what isn't the device or the measurement system that you're measuring with. So it is absolutely critical, and you can't be afraid to go through there and actually build custom fixturing that will allow you to dynamically change the temperature in the environment so that the unit that you're trying to test is at a specific temperature, and make sure that the temperature across the entire unit is uniform, and have all the measurement system, including the cables, outside of that environment where it's not affected by the thermal environment that you're making the test at. So fixturing, it is critical in actually getting an accurate measurement for thermal stability.
Okay, so then I assume that there are various ways to design for achieving thermal stability.
Yes. So now that we talked about, the criticality of measuring it, and keep making sure that everything that is in the measurement system is outside of the oven. Things that are in the oven, dielectrics, for example, can change dramatically over temperature depending on the particular material that you're picking up here. So dielectrics, for example, can change the dielectric constant of a material, can change over temperature. Most PCB materials that are readily available today do have some variability over temperature. Teflon is something that is widely used in the industry, varies significantly over temperature as far as its dielectric constant is concerned. These sorts of changes can change fairly dramatically insertion phase on units, just due to the propagation speed difference of the changing of dielectric constants. Can have a big impact on insertion phase. Other parameters, such as VSWR, are due more to not necessarily propagation speed changes due to dielectric changes, but rather due to the fact that if we're changing the dielectric constant, the reflection coefficient is going to change a little bit, which changes the VSWR. So VSWR gets affected. Isolation and directivity come into the fact that if you're into a coupled line structure, for example, where you have an even and odd mode balance within the material, you have to have a good equalization of in order to get good directivity. As soon as one of those dielectric constants change a little bit, that balance gets disrupted, which affects directivity. VSW isolation and things like a power divider, for example, are affected a little bit because the VSWR is affected. So there is this very high interplay going on between the dielectric constant and all of the electrical parameters. The thing that we talk most about is phase change, but that is something that is really critical for all the parameters, really. Another constant that changes due to in dielectrics is the loss tangent, the material loss tangent. This really affects insertion loss, and we see this on passive devices all the time. As the temperature goes up, so does the loss tangent, and therefore the insertion loss gets higher. As the temperature gets colder, loss tangent gets better, insertion loss gets less. If you're looking at a system with differential lengths in there, that can affect things like amplitude balance as well. So these are things that are undesired effects of temperature. The other thing also that you have to keep in mind also is that the thermal conductivity of metal changes over temperature. Again, this directly affects insertion loss, and it works in tandem with the dielectric loss tangent within passive materials. So this really has a way, an effect, that can be negative if not mitigated. So what we have to do here as we're designing these components is we have to make sure that we look at all of these thermal constants with the materials that we select. We try to minimize the variability within the materials that we select to get the best performance over temperature. Some materials work better over certain temperature ranges, and material selection is key in designing for thermal stability. So this is really where we're at here now. It's all about controlling the variables. So the raw PCB material selection, it is critical to make sure that we have the dielectric constant variation under control, the dielectric loss tangents, and then the thermal coefficient of expansion, the CTE. The mechanical stack up, especially in a strip line coupled line structure, the amount of residual airspace in a mechanical buildup of PCBs makes a big difference in the even odd mode balancing. So therefore, the amount of thermal expansion within those materials affects the electrical performance of those materials over temperature. So this is something that really it has to be very, very carefully monitored to make sure that we mitigate those and control those. Ohmic conductor losses are a little harder to control. Those are just based on materials. So again, it's about material conductor selection that really gets involved here. Also, plating that we put on these conductors also leads into the impact of how much loss that we get over temperature. Some platings have a higher reactive over temperature than others. Typically, we want to stay away from nickel and those sorts of things. They tend to vary more over temperature. We like to stay more with copper and silvers from a stability standpoint for conductor ohmic losses. I sort of touched on this already about the mechanical assembly properties. I can't stress enough how important it is to get a good solid mechanical layout to make sure that the compression changes that we get in strip line assemblies to go through there and actually have those controlled. Also understanding the material that we use for physical link changes. The physical link changes, aluminum, for example, expands and contracts, and making sure then that all the other materials that you have around it work in unison, essentially, to make sure that we can mitigate those sorts of thermal activities. A big piece of what we try to do within to help mitigate a lot of thermal stability questions has to do with thermal equalization. For a lot of systems, the absolute throughput time or delay or phase of a particular unit very often is not the driving factor, but rather how well does it track with another part of the system. So a lot of systems that are designed really have to do with tracking and how well one part tracks relative to another. To accomplish this, it's all about mechanical thermal equalization, as well as, which is basically designing the part to make sure that we have equal thermal transfer throughout the part, or equalizing the mass around these various pieces. This way, as the units heat up and cool down, that the temperature of the various dielectrics that are changing will be the same for one side of the unit versus the other side of the unit. And this is really critical with design for thermal equalization. Really a lot of detail needs to be paid attention to, and this is something that I think that TRM really excels at in our designs.
Wow, so you really need to anticipate a lot of variation here. So great information as always. Can you maybe just summarize?
Certainly. The key here really is material selection. I can't stress this enough. There are certain raw parameters of materials that you just can't get away from. So you have to make sure that the material that you're picking is suitable for the environment, and that its thermal coefficients are understood. Again, the next bullet down there, understanding the application is also critical, and actually figuring out the best way to mitigate thermal instabilities. Phase changes will happen. The question really is, how are you going to manage that? Can the system tolerate some phase changes if it's consistent across the part, and if the phase changes track? Some applications will you can use that to your advantage. Other applications, it's an absolute thing. You have to make sure that you mitigate the thermal tracking. So understanding those trade-offs are critical in being successful here. And the other thing also is being able to measure it. You have to go in there and have enough tooling and fixturing in place to be able to accurately measure just the unit, and remove the entire test setup, including cables, from that measurement, so that you're not fooling yourself into thinking that you have a good solution. Cables can run and make things look worse. Depending on the way that the cables run, they could mask some problems as well. So it's not always a worse than situation by adding a cable in there. Sometimes they actually make it look better than what it really is. So the whole idea here is to make sure that what you're getting is accurate information by custom designing the measurement system to be able to only measure the unit that you're looking for.
Okay, so now that we understand better the importance of design and measurement, could you maybe tell us a little bit about some of the differentiators?
Sure. So what TRM really thrives with is we want to work with our customers and really be the solution provider for your needs. We will go through there. We will carefully select materials. We will do robust packaging, outside the box packaging, if that's really what the project requires. And we will supply whatever objective evidence that is needed to be able to make sure that the part is thermally stable or meets the other requirements of your program, whatever that may be. Like I said, TRM is a solution provider that wants to work with our customers, make sure that they get the components that they need so that they can be successful.
Okay, and we do have a question. And it's something that I kind of wondered as I was listening today, because you talked a lot about thermal stability. So do other environments beyond temperature impact stability?
Yeah, absolutely. And I think that jumps to mind here, Paul, is the air pressure, or altitude stability. One thing I think that we kind of take for granted is that the environment is always going to have air around it. When you go up high in altitude, that is no longer the case. So stability for things like power handling vary widely when you change the air pressure. So I think that is one thing I think that you definitely have to think about. Other parts for stability are mechanical stability for other sorts of shock and vibration environments. So every aspect of environmental testing that a unit can be subjected to has its element of stability associated with it, and they're all critical. These devices have to operate in very severe conditions sometimes, and sometimes in a variety of conditions. It's not just, gee, it's getting a little warmer, it's getting a little cold. Sometimes it's getting a little cold and all the air is being sucked out of it. All the combinations of all these environments are critical, and it's something that we always take into consideration as we're building and designing these components.
Okay, well, maybe we could think about addressing some of the ways that these other environments need to be anticipated and how you design for them in a future session. But I guess for today, thank you, Shaun, and thank you all for joining us. If you are a customer and you have more questions, or if you'd like to discuss details for some of your programs with one of our engineers, we'd love to hear from you. Please feel free to call the engineering hotline. The number's on your screen. As I think you know, there are no costs associated with these conversations. And if you're one of our field sales representatives, then you know that your calls are also welcome. You can also submit questions directly through the sales rep portal on our website. And in case it's helpful, our next Tech Talk will be on Tuesday, April 26th at 1 p.m. And the topic will be determined shortly. So thank you again, Shaun. Always a pleasure.
Yep, thank you.